I have this article here on warm exotitans as a test of planetary atmospheric diversity. Ooh. You will have an opinion. Well, now I don't want to forget to ask him. I'm so curious on the opinion. I'm not adding like too much humor into it, but I do have one joke in it that I feel like is really, really good. But I feel like you might have to be like a streamer or like know the Twitch community slash like Twitch jokes as a whole to get it. And I'm not entirely too sure how the audience will be, but I think it'll hit. I think it'll hit. I just did it either way. I was like, if no one laughs at this, it's fine because I think it's funny. I did it for myself, but I hope it hits, you know? Okay, Shrum has the spot for the Reuben sandwiches. Is that a warm exotitan in your planetary atmospheric diversity test? Or are you just happy to see me? Wow. What a lovely Kappa emote there too. Wowie. Oh my gosh. So, this is from Universe Today. It was from like 2 days ago, or yesterday. What can exoplanets orbiting M-dwarf stars teach scientists about planetary formation and evolution? That is a artist rendition of some exoplanets around an M-dwarf star. So this is what a recent study posted to the archive preprint server, submitted to the American Astronomical Society Journal, hopes to address as a team of researchers investigated the possibility of exotitans, exoplanets with atmospheres comprised of nitrogen and methane like Saturn's moon Titan, orbiting M-dwarf stars, which are smaller and cooler than our sun. The study has potential to help scientists better understand the formation and evolution of exoplanets orbiting M-dwarfs and whether they could possess life as we know it. For the study, the researchers used a series of computer models called photosem to simulate photochemistry on exotitans, specifically estimating the lifetimes of atmospheric methane. Along with methane, the models examine the presence of hydrogen, nitrogen, oxygen, carbon, which are part of the photosem network, and also some, important molecules and ingredients for life and things there too. Additionally, the team used the exoplanet TRAPPIST-1e, which orbits an M-dwarf star, as part of the model by treating it as an exotitan. In the end, the researchers found that the methane on the exotitan, on an exotitan TRAPPIST-1e, would have very short lifetimes, along with estimating between a 1 to 10% chance of astronomers detecting a warm exotitan. Intriguing. So the study notes, this finding is consistent with recent JWST non-detections of methane-dominated atmospheres on warm terrestrial exoplanets. The low prior probability means that the standard of proof required to claim a warm exotitan detection is high, and we offer specific suggestions towards such a standard of proof. Observation of oxidized carbon species would corroborate a putative warm exotitan detection. Confirmed detection of warm exotitans would signal the need to fundamentally rethink our understanding of the structure, dynamics, and photochemistry of Titan-like worlds. As noted, TRAPPIST-1e was chosen for the study since it orbits an M-dwarf star, the latter of which are increasingly getting attention for their exoplanets potentially being habitable. While TRAPPIST-1e takes only 6.1 days to complete one orbit, for context, Mercury takes 88 days, it is orbiting squarely in the middle of the star's habitable zone, making it an ideal target for astrobiology and the search for life beyond Earth. Indeed, I was talking about TRAPPIST-1 a little bit earlier on stream, and it does orbit really fast, but you can't really compare it to Mercury's orbit because TRAPPIST-1 is a red dwarf star, so it's a lot smaller and a lot cooler. All of the planets, all 7 planets around TRAPPIST-1 orbit way closer than Mercury orbits to our sun. And therefore the habitable zone for them where liquid water could exist on the surface is also a lot closer. Like it says, only 6.1 days to orbit around. Additionally, M-dwarfs have a much longer lifetimes than our sun, potentially reaching trillions of years compared to the 10 billion year lifetime of our sun. This much longer lifetime could enable their exoplanets to develop the necessary components for life as we know it, or even life as we don't know it. Ooh, cool. The complement using TRAPPIST-1e as an analog, the researchers chose Titan as an analog due to its potential biosignatures like nitrogen and methane, with methane being the dominant atmospheric composition of Saturn's largest moon. Titan has long been hailed as a target for astrobiology due to these biosignatures, with past studies even suggesting it could mimic conditions that were present on ancient Earth. While Titan orbits much farther beyond our sun's habitable zone, a potential exotitan orbiting within its star's habitable zone could provide a unique opportunity for astronomers to finding life orbiting an M-dwarf star. However, if the findings prove to be correct regarding the low probability of finding a warm exotitan, which, it said finding life there might not be the case. Once again, their probability for that was like 1 to 10% chance of finding a warm exotitan based on their models, kind of using TRAPPIST-1e as a analog for it. The study comes as the number of confirmed exoplanets recently reached 6,000. We're over 6,000 confirmed exoplanets and over 9,000 exoplanet candidates, too, that need to be confirmed, which is so exciting. Also, along with NASA preparing to send its Dragonfly quadcopter to Saturn's largest moon, which they are talking about Titan, which is currently scheduled to be launched in July of 2028 and an estimated arrival date at Titan of 2034. Therefore, studies like this can help astronomers better understand what types of exoplanets exist throughout our universe and whether they could be habitable for life. It's nice to know what kind of exoplanets could exist and like what to look out for, and obviously where to kind of look if we're looking for life out there. It is kind of a needle in a haystack, and it's nice to know if there's a specific direction or a specific area of the haystack, you know? Maybe what the needle might look like could help. But yeah, all of this stuff kind of helps us learn a bit more about that. And even when we get more data and different things, some of these models and other stuff might make it kind of easier to sort through that data once we get it as well. So yeah, all of these updates I think are always exciting and interesting. Yeah, this is on the archive preprint server, but I think it said it was submitted to American Astronomical Society journals. So yeah, I don't know if it's been like peer reviewed or anything like that, but kind of interesting to see what they're doing and what they're getting up to. I really love exoplanet science and all of the cool stuff they do. If I were to I feel like that's something I would like to do like research on or something one day, maybe, of like exoplanet atmospheres and just this kind of stuff, the atmospheric diversity and everything. I would love to check into that more. Also, obviously, the watery moons in our solar system is another big favorite of mine, especially, maybe doing sample return missions one day. So an exoplanet is just a planet orbiting any star outside of our solar system. So any star that's not our sun. They will say that it's in the habitable zone or in the Goldilocks zone if it is. So exoplanets can be anywhere, like in the orbit around the star. There's even exoplanets that don't orbit a star. They're called rogue exoplanets. But yeah, if they're in the habitable zone, it'll say like a habitable zone exoplanet, or maybe even like a potentially habitable exoplanet. But yeah,